Hello, everyone. My name is Dr. Mohammed Zeshan Azam, and I'm working as an assistant professor in chemical engineering department. I am affiliated with the chemical engineering department of Wa Engineering College, University of Wa. I'm working here. It's been 1 year I've been working here, and today I'm going to present a topic that is very, common in chemical engineering subjects and very helpful for the students. So it is uh, Henry's law and Raoult's law that is usually used for the vapor liquid equilibrium calculation. So we will begin with this. First of all, I would like to introduce what I'm going to represent, and then I will discuss the mathematical expressions and the details where we can use it, what are the limitations of these law, and so let's begin. First of all, we have Raoult's law. If you see here, Raoult's law means, what does that mean? Concept. Both law, mean Raoult's law and Henry's law, describe how much of a chemical is in the vapor phase compared to the liquid phase. The difference depends on how concentrated the species is. What does that it mean? That when we have mixture of a liquid and their equilibrium with its vapor in the vapor phase. So if we know some, a temperature and the composition of one phase, like liquid or gas phase, we can calculate the other phase that will be in equilibrium position. For example, if you know the liquid composition, you can know by using the Raoult's law and Henry's law, you can calculate the second phase composition. So the difference between and how concentrated the species is. So let's focus on the mathematical expression first of all. We have YIP equals XIPI saturated. What does that mean? Let me explain it to you. Yi means the vapor phase composition of component I. I can be any component. It can be benzene, it can be water, it can be alkanes, alkenes, and Yi depends on the species. The species in the gas phase. What will be the composition of that species in the gas phase or vapor phase? And P is the total pressure inside the vapor phase. So we have to mention it that P is representing here the total pressure in the vapor phase. Okay, and let's go ahead. And here we can see this product will be equal to Xi. Xi is the liquid phase composition of the same component, and Pi saturated here is the saturation pressure. I mean, what will be the saturation pressure at these temperature pressure conditions? So saturation pressure can be calculated in two ways. First, we have if it is water, then we can use the steam tables. We will have the temperature, and against that we can find the saturation pressure. For example, in steam table, you have given the temperature. So at a certain temperature, the saturation pressure will be given in the steam table. So what does that mean, the saturation pressure? Let me explain it to you. So saturation pressure tells that is basically the pressure at which water boils at at that certain temperature. So if you know the temperature, for example, let me give you an example. We have water, and water has 100 degrees C, uh, the temperature. What will be the saturation pressure? I mean, what will be the saturation pressure when water will be at 100 degrees C? Saturation pressure mean boiling, where water will be able to boil. So 100 degrees C is able to boil only if the saturation pressure is 1 atm, right? So it means we have saturation pressure here is 1 atm, right? Okay, this is the one way to calculate saturation pressure if we are using water. Okay, now if I'm not using the water, I'm using something else, for example. Okay, so the other way to find the saturation pressure is the Anthony constant. You can have Anthony constant in this way, A, B, and C. So in this A, B, C, these are specially calculated for each component. For example, if you're using benzene, the Anthony constant will be different. And if you're using toluene, the Anthony constant will be different. And it will be given in special uh, pressure range. So what is the pressure? Uh, sorry, what will be the temperature? And it is temperature dependent. So when the Anthony constant is given, the temperature range will also be mentioned. For example, 40 to 70, 40 to 400 Kelvin. So this is the second way um, we can use to evaluate saturation pressure. So here, the saturation pressure can be calculated from the Anthony constant or from the steam table, and P can be calculated is the vapor phase pressure, easily calculated by the gauge pressure. Yi is the composition, Xi is the composition. So one of these composition is usually given to calculate the other composition. So now let's go ahead when we can use it, when to use this for the solvent. I mean, when the concentration of a component is high in the liquid, we use this uh, Raoult's law. And we will see in the Henry's law, when the concentration is dilute, I mean, like water and carbon dioxide in water is very, very low dilute form, CO2 in water. So what we will use it, Raoult's law or Henry's law, we can say that we will have to use Henry's law because CO2 is very, very low solubility in water. So that is why we will use Henry's law. So now we have covered this Raoult's law and Henry's law. It is the same as the Raoult's law. The only difference between it is the saturation pressure. Here we have to find the saturation pressure, and here we have to find the Henry's constant. Yes, in the literature, all of the species have given Henry's constant, so we can use it Henry constant here, and we can find the composition. So use this for the solute. The component that is very dilute, Xi almost equal to zero, like CO2 gas dissolved in water, the same example I have given you. The simple meaning is that for a tiny amount of gas trapped in a liquid, its a push into the vapor phase is proportional to the specific constant, Henry's constant, instead of its pure vapor pressure. So I think from this slide, we are clear what are Raoult's law and Henry's law and how we can use it to calculate. So in the upcoming slide, we will try to give an example to calculate different composition. So this is the further detail where the significations, Raoult's law, modified Raoult's law, and Henry's law. So what are, I mean, the same explanation that we have given, the component can be more than 1 to 2, n. So Y1P is equal to X1P1 saturated. If the component are 2, we will use Y1P plus Y2P equals X1P1 saturated plus X2P2 saturated. So where Xi is the liquid phase mole fraction, already have been told you. Yi is the vapor phase mole fraction, already discussed. Pi is the vapor pressure of pure species at the temperature of the system. So we can say vapor pressure or saturation pressure. It is the same if we are talking about the pure species. The pure species must be. Okay, the product YIP is the partial pressure of species I in the vapor phase. Yes. So now what are they telling you? That YIP is basically making the partial pressure because this is the total pressure and this is the mole fraction of that species in the gas phase. So when they will be multiplied together, we will give us with partial pressure. So this partial pressure is tell you partial pressure is what the individual pressure exerted by a individual species. So we call it partial pressure, right? So we can also use it in the the complex numericals. We can use this yip is equal to pi directly. So we will not have to confuse it, right? So note that only thermodynamic function to survive here is the vapor pressure of pure species, suggesting its primary importance in vapor liquid equilibrium calculation. So I think these are the slides which are given. Yeah, here we can say something different, phi I and gamma I. What does that mean? It means that these are basically the correction factors. We call it Vygotsky coefficient and we call it activity coefficient. Where we use it when we are talking about the real conditions. I mean, if you are teaching or if you are at a undergraduate level, I think this is enough for you to know that for ideal gas condition, phi I equals 1 and gamma I also equal 1. That is why we use it for ideal solution, right? If the solution is not ideal and we are technically want to know what actually the interactions between the molecules, we call it, we use it phi I and gamma I. Then we have to go a long way, different, like based on cubic equation of state. Cubic equation of states we use to evaluate different Vygotsky and you know, the activity coefficient. So equation of states are used because equation of states gives us the compressibility factor, and from that we can calculate, and we have different types of expression based on the equation of state, not directly from the equation of state we calculate it, right? So I think we are clear about this slide. Let's go ahead. Yeah, this is the case where Raoult's law and Henry's law is used. We have here is the liquid, and here we have the partition. I could, yeah. Here we have the partition, and here we have the liquid phase, and here we have the vapor phase. If we know the liquid phase composition and temperature, we can find the other composition of the vapor. So you can be asked during exams or interviews that this is the temperature and this is the composition. What will be the temperature composition in the vapor phase? So you can be calculate by using that, or you can, if you are in an interview, you can say that you can use Raoult's law or Henry's law, depends on the concentration of the solute and solvent, right? So let's go ahead. Okay, if we take it very simple way, uh, define the very simple way, what is Raoult's law? We can say it is a simple mathematical bridge that connects the liquid phase to the vapor phase. So because practically, if you see, we cannot go and see inside and check what is the vapor composition, what will be the liquid composition. No, because these all are going on inside the pipes, inside the reactors, inside the different types of equipments. So we cannot, check it directly, or we can insert it the composition finder into it and taking sample again and again. No, we cannot do that. So best way is to calculate it by different approaches. So let's go ahead. Modified Raoult's law. Okay, what is the modified Raoult's law? The only difference modified Raoult's law and ideal Raoult's law is the gas. I mean, ideal or real. If you're using ideal, then you will be used Raoult's law, simple Raoult's law for ideal. And if you're using real, I mean, if you want to know real interactions of molecules and their effect, then we can use modified Raoult's law, right? So this is the simple. And what will be the difference between ideal and Raoult's law? Mathematically, we have phi I and gamma I. So it will differentiate phi I and gamma I. This is for the gas phase and this is for the liquid phase. What is this basically? These are basically the coefficients work as a correction factor, that what will be the effective value of that parameter. Though standard Raoult's law assumes ideal behavior, where molecules of different chemical like each other exactly as much as they like themselves. So in reality, molecules often have stronger or weaker interactions. So these value can be different because of different interactions. If the interaction is strong, the value will be different, and if the interaction is weak, the value will be different. So in any case, it will not be ideal. In the real case, it will always be different from the ideal. Okay, the here we use gamma, right? So if gamma greater than 1, the molecules dislike each other. It means if value of gamma, it will be calculated based on equation of state different mathematical expression. The molecule dislike each other. I mean, there are attractive forces or repulsive forces. Obviously, if they are dislike each other, they have more dominant repulsion forces. And similarly, if they are more attractive forces, then what will happen? Gamma will be less than 1. But we have to calculate what will be the value of that less than 1, right? So we are not getting into it right now because we are here explaining this basic Raoult's law and Henry's law and their usage. So let's go ahead. Why it matters? Standard Raoult's law is excellent for very similar chemicals. And let me erase it first. Okay. Yes. So standard Raoult's law is excellent for very similar chemical like benzene and toluene. I mean, we can use standard Raoult's law. I mean, we do not have to go to the modified Raoult's law and go for the complicated, calculation. We can go standard Raoult's law for those chemical which have very similar chemical identification like benzene, toluene. They can easily mix each other. So Raoult's law, modified Raoult's is essential for mixture like alcohol and water. They are totally different, where the chemical attraction repulsion changes the boiling points and equilibrium significantly. So what does that mean? When we will mix those chemical having difference in the makes the difference boiling point very low. I mean, there are no significant making impact on the chemical properties of the mixture, then we can use it standard Raoult's law. But if like alcohol and water, if the chemical attraction repulsion changes the boiling points and equilibrium significantly, if there is the significant effect, obviously then we will have to use modified Raoult's law. So I think we are clear about modified Raoult's law now. Now look at this example so that we could understand what is this. And this is basically the implication of that. Assuming that carbonated water, CO2 and H2O, determine the composition of the vapor and the liquid phases in a sealed can of soda at 25 degrees C if the pressure inside the can is 5 bar. So from here, one thing we can understand is that CO2 and water. CO2 has very low solubility in water, right? So determine the composition of the vapor and liquid phase in a sealed can of soda. The temperature and the pressure and the temperatures are given. So to know the vapor composition, we will use Henry's law. To know the liquid composition, we will use Raoult's law because CO2 in water is very low, right? So let's go ahead and find it out. Okay, expecting that the liquid phase will be nearly pure water. Do you agree with that? Because CO2 is almost very low solubility in water, so we can assume that it will be nearly pure water in the liquid phase, right? The vapor phase will be nearly pure CO2. The same case for the case with we apply Henry's law for CO2 and Raoult's law for water because water is as a solvent and CO2 as a solute and CO2's solubility is very very low. So we can assume use Henry's law for CO2 and Raoult's law for water. If you're clear about it, then we can go ahead simply and we can use the same mathematical expression that has been represented in front of you in previous slides, y1p, x1h1, y2p, x2p2 saturated. I mean, there is no question of this mathematical expression. Let's go ahead. X1 is equal to y1p over h1 and H1 will be given. Is I think here it's not given, but it must be given, or we can use the literature. Literature must be given if you are solving this question. Henry's constant, right? So you do not need to calculate individually. So 1670 is the Henry's constant. Where you will see in the CO2 in water, Henry's constant. So 5 over 1670, you will get x1 is 0.0030. Once you get x1, you can easily calculate x2, right? 1 minus x1. As we know, x1 plus x2 equals 1, right? So let's go ahead. Similarly, with the liquid phase, we know the liquid phase is nearly pure water. So we have Y2 is equal to X2P2 saturated over P. So X2 P2 saturated saturation pressure of water, P. So we can use the steam table to calculate saturation pressure if it is not given. So we can use, yeah, from the steam tables, the vapor pressure of water at 25 degrees Celsius is 3.166 kilopascal or 0.0317 bar. Therefore, Y2 is equal to 0.0317 divided by 5. So, from the steam table, which steam table we will use? The saturated water. Because water here is saturated, so we will use the saturated section of the steam table to see the temperature, and then we will see the saturation pressure. So at the given temperature, that is 25 degrees Celsius, we have seen from the steam table, we have the 0.0317 bar. We will use this, and consistent with our expectation, the liquid is 99% 0.7% water and the vapor is 99.4% CO2. So from this calculation, now I will sum up the lecture and I will tell you that Raoult's law, Henry's law, and modified Raoult's law. What are these? What are their limitations? Or what are their usage? And how can we proceed to calculate different composition in vapor phase or liquid phase, right? So I give you this as an assignment. You can go ahead and find out. We have pair of different parameters, like we have given A, we can give an x1 and t is equal to 100 degrees C. Find y1 and p. How will you find y1 and p when x1 is equal to 0.33? So one thing is clear, x1 is 0.33. It means it is significant amount. So we cannot use Henry's law here, right? And 100 degrees C, we can find saturation pressure as well. And here is the benzene and toluene. So we are clear that we cannot use the steam table. No, because steam table is only used for water. So what we can use here, we can use Anthony constants to calculate saturation pressure. So once we have Anthony constant ABC form, we can go ahead and find out the required parameter like y1 and p. So I hope all the students who have attended this lecture will be able to use the knowledge and can be able to solve all these questions asked. Whilst Raoult's law to be an excellent VLE model for this system at the computed condition. So you have to give the reference of modified Raoult's law or standard Raoult's law. Thank you so very much for having with us. Allah Hafiz.